Hello everybody. In this session, I'll discuss the electronic configuration of elements. Okay. So electronic configuration is the uh, distribution of electrons in the main orbit. In turn, it is in the suborbits also. So usually the electronic configuration of the elements are expressed in the form of a sequence. For example, I'll give the example of the sodium. The atomic number of sodium is 11 and that can be written in this manner, that is 1s2, 2s2, 2p6 and 3s1. So the totally 11 electrons are there. And we know that according to Pauli exclusion principle, the first orbit can be accommodated with only 2 electrons and the second orbit will be accommodated with 8 electrons. So based on that, this number indicates the orbit number. Okay. So this indicates the subshells which are present in the each of the orbits, and this number indicates how many electrons can be accommodated in this suborbitals. Okay. So the among 11 electrons of the sodium, the first 2 electrons are accommodated in first orbit and the 8 electron will be accommodated in the second orbit, and the last electron is accommodated in the third orbit. So usually if you write the electronic configuration in this sequence manner, it will become very lengthy for the case of atoms with the higher atomic numbers. So in such cases, we can abbreviate the same electronic configuration in terms of noble gases. Noble gases are nothing but a helium, neon, argon, krypton, xenon, and radon are the noble gases in which the orbitals are completely filled orbitals are present. Therefore, we can express, instead of writing the lengthy electronic configuration of the elements, we can express the same thing in terms of noble gases also. So the noble gas, I'll express the sodium in terms of neon gas now. Okay, the atomic number of the neon is 10. So up to here, I can express it as a neon, and that can be taken in a square bracket. You see, I'll show you the sodium expressed in terms of neon in this manner. Okay, see here. The same sodium can be expressed as neon and 3s1. Only the last electron can be right. Similarly, silicon. I can give the example of silicon also. The silicon atomic number is 14. Okay, as the atomic number of neon is 10. So silicon electronic configuration can be written as neon 3s2 and 3p2. Okay, 4 electrons will be left out now. So the electronic configuration of the silicon can be written as neon 3s2 and 3p2. So in this way, the lengthy atomic number can be expressed in the uh, terms of noble gases. Okay, what is the use of the writing this electronic configuration? The electronic configurations are useful in determining the valency of an element. That is, how many electrons are present in the outermost orbit. If you know the valency of an element, we can predict the element belongs to which group, because 7 groups are there in the periodic table. So the element which comes under which group can be decided just by looking into its valence electrons. So, and also in turn it helps in understanding the atomic spectra, because one group of elements will exhibit a similar type of atomic spectra. So these are the some of the uses that we have with the help writing a electronic configuration. We can understand these things here. So usually electronic configurations are written based on 3 principles. The one is of Bow principle, the another one is Pauli's exclusion principle and Hund's rule. So let us understand in brief the what is the of Bow principle. States that the term of Bowin belongs to the German, and the meaning of this is build up. That means how the atom, that is electrons, can be built up in the atom. So based on this principle, one can write the electronic configuration. So based on this principle, the diagram usually what we follow to write the electronic configuration is given here. But one thing is, so few elements will deviate from this also. Okay. So especially the chromium and copper, I'll discuss at the end of this video. I will show you how it is going to deviate because of its stability. Now you see, because of the stability provided by half filled or completely filled subshells, these chromium and copper are slightly deviating from the of-bow principle. Okay, so the another principle we used to we used in writing the electronic configuration is Pauli's exclusion principle. That is, according to Pauli's exclusion principle, we know that the maximum number of electrons accommodated in each main orbit is in accordance with 2n square rule, and in each subshell the electrons can be accommodated, the maximum number of electrons can be accommodated is 2 into 2l plus 1, where l is the orbital quantum number. The another principle we are using to write the electronic configuration is Hund's rule. Okay, so this rule describes the order in which electrons are filled in all the orbits of the subshell. So this rule states that uh, every orbital in a given subshell is singly occupied, okay, by the electron before the second electron is filled in an orbital. That means, now you see, this is the example what we have taken here is for carbon. Okay, carbon, the atomic number of carbon is 6 here. So the first two electrons automatically goes to the first orbit. Okay, so with a pair here, the next four electrons will be left out in the second orbit. So the accommodation of the electrons is not in this fashion. Okay, two electrons will go to S subshell and two goes to P, because the capacity of the P is 3 here, means 6 electrons it can be accommodated. Both the two electrons will not be accommodated in the P shell like this. Instead, it is going to be accommodated. First, it will be distributed in the single electron. Then the pairing will start for the subsequent suborbitals. So these are the three rules followed for writing the electronic configuration. Now I'll mention few electronic configuration of the few elements is mentioned here based on of-bow principle. Okay, so the carbon 6 we have written as the first is 1s2, the two electrons, the capacity of s is 2. Okay, and next two electrons will be accommodated in 2s2, and the next two electrons are left out, and that should be accommodated in p subshell. Actually the capacity of p subshell is 6, so out of 6 only 2 electrons are filled here. Okay, similarly the neon already have given in the example itself the electronic configuration. So according to this, 10 electrons are there, 2 here, 1s2, 2s2, so totally 4 are accommodated, and 2p6 as the capacity is 6 here, 2p6. So this completes the electronic configuration of neon. So next, aluminum I have mentioned here based on the same thing I have written, and I told you while giving an explanation that some of the elements will deviate from the of-Bose principle, that is chromium and the copper. Just you observe here, the atomic number of chromium is 24. Now you see, according to this, after 1s2, 2s2, 2p6, 3s2, 3p6. So after 3p6, it is not accommodated in S subshell in the fourth orbit. Okay, so the 5 electrons are accommodated in the D suborbitals. Then the next single electron is accommodated in 4s, because the capacity of the D is 10 electrons. So first we have to give all the single electrons, that will be 5 electrons will be given. Then instead of giving the pairing in the D itself, it should be given to the 4s. Then we should come back just to maintain the stability, and also the energy levels we have to look into for that one. So even the copper is in the same fashion we can get. So first it is going to fill all the 10 electrons in the D, then the remaining electron will come to 4s. So this is the how the simple method has to be adopted in writing the electronic configuration. Thank you very much.